So thank you so much for having me, and thank you so much for organizing. So I'm going to be talking about some recent results of myself and Antonio Jourao in the world of randomly perturbed graphs. So I guess before I go into talking about perturbed graphs themselves, I should mention a few background results. So of course, I assume that everyone here knows what a Hamilton cycle is, but just in case, whenever I talk about Hamiltonicity, I just mean the property of containing a Hamilton cycle, which is a cycle that covers every single vertex of a given graph G. And then in general, in combinatorics, when we try to find certain structures in graphs, there are several perspectives that we can take, but there are specifically two that I'm interested in, which are the more extremal one and the more probabilistic one. So in the extremal one, we basically want to find some deterministic conditions that guarantee that we satisfy some property. And in the case of Hamiltonicity, there's this very well-known result of Dirac, who proved that if we have some graph on n vertices and the minimum degree is larger than n over 2, at least n over 2, then G must contain some copy of a Hamilton cycle. And this result is best possible because you can take a complete bipartite graph which is slightly unbalanced in such a way that your minimum degree is n over 2 minus 1, and this graph cannot contain a Hamilton cycle. So this really is the best that you can do. So that's it for the extremal perspective. I mean, that's it. That's one example. And then there's also the probabilistic perspective, where we're more interested in typical properties of graphs. So if, for instance, I consider the GNP model, where the idea is that we start with a set of n vertices and we add each of the possible edges with probability p independently of all the other ones. The main question would be, for which range of p is it true that GNP is very likely to contain a Hamilton cycle? And this question was answered by Korshunov in the 70s. And what he proved is that as soon as the probability is slightly larger than log n over n, then with very high probability, GNP contains a Hamilton cycle. And again, this is best possible in the sense that if the probability is slightly less than log n over n, then with high probability, GNP has a few isolated vertices, and therefore it cannot have any Hamilton cycle. So somehow we have these two very different results, and both of them are best possible in the sense that you can't improve the minimum degree condition on Dirac's theorem, and you cannot lower the probability for Korshunov's theorem. And the idea is that randomly perturbed graphs try to combine these two types of results into a single statement. So we're going to try to combine minimum degree bounds and some probability. So the idea is that we're going to take the union of two graphs, one of them deterministic, let's call it H, and one of them random. And for this talk, I'm only going to consider deterministic graphs that satisfy some minimum degree condition and random graphs that use some probability that is somewhat lower than the threshold. So you should think of this alpha n here with alpha being lower than 1/2, because in the case of Hamiltonicity, this means that H does not necessarily contain a Hamilton cycle. And if G has probability lower than log n over n, then with high probability it will not contain a Hamilton cycle. And the main question is whether, when you take their union, you can somehow guarantee that you will find a Hamilton cycle with sufficient high probability. So this direction of research was started by Bowman, Fries, and Martin in the early 2000s. And they studied precisely this property, Hamiltonicity. And what they proved was that if alpha is any constant, then the union of a deterministic graph with minimum degree at least alpha n with a random graph that has probability at least constant over n, where this constant depends on alpha, with high probability is Hamiltonian. So the big improvement here is that rather than needing log n over n probability, it's enough to just have constant over n. So there's a logarithmic improvement on the needed probability. And very recently, this was generalized by this list of authors, so Han Klimer, Maesaka, Moge, Moore, and Parchik. And they basically proved the same thing, but allowing alpha to not just be a constant, but some function that goes to 0 with n. And what they proved is the same type of result. So the probability has to be at least the logarithm of this alpha divided by n. So the reason why I say that this somehow bridges the gap between extremal results and probabilistic results is that you can think of it two ways. You can think about it as fixing some minimum degree alpha n, and for each possible value of alpha n, you want to find out which minimum probability you need to ensure Hamiltonicity. And you can also think of it in the opposite way, where you start with some probability and you ask whether there is some minimum degree condition that guarantees that the union of the deterministic graph and the random graph will be Hamiltonian. So this is basically the framework that we're working with. And I should say that since Bowman and Fries and Martin started studying this, there has been a very large amount of research on this topic. So for instance, Krivelevich, Kwon, and Sudakov studied pancyclicity, which is the property of containing cycles of every length. So we say that a graph on n vertices is pancyclic if it contains a cycle of every length between 3 and n. And then different authors have also considered powers of Hamilton cycles. They have also considered F factors for different graphs F. They have considered different types of spanning trees, and they have considered some very general results about bounded degree spanning subgraphs in some sense. And okay, so all of these results that I have listed here, I'm obviously not going to go into any details with them, but they're all for random binomial graphs, which is the GMP model that I just introduced. But also some of these problems have been studied in random binomial directed graphs, or in random binomial hypergraphs, or also in random binomial subgraphs of the hypercube. So there really is a very rich literature by now. But somehow the thing that I want to bring to your attention here is the fact that in all these studied models, there's a keyword which is binomial, which appears everywhere. So somehow almost every result about randomly perturbed graphs deals with random binomial graphs. And I think a natural question is, what happens if we consider other random graphs which are not binomial, and what can we say in these other instances which are also natural? And in particular, the one that we decided to study together with Antonio was random regular graphs. So random regular graphs, I should say that, okay, so to be clear with the notation, whenever I write G and D, what I mean is that we take a D-regular graph on n vertices, and the way to choose which graph in this random setting is just to consider the set of all these graphs and pick one uniformly at random. So of course, there are some divisibility conditions to ensure that such a graph exists. So for instance, you need n times d to be even. But as soon as it exists, this is a very rich model of random graphs. It's a bit harder to study than binomial graphs because edges are not independent anymore. So an important feature here is that if you condition on some edge being in the graph or not being in the graph, then the probability distribution of all the other edges changes a little bit. But despite this increased complexity when studying this model, it has actually been very, very thoroughly studied, and there are some very, very interesting results. And in the case of Hamiltonicity, which is what I'm talking about, there is a very, very sharp theorem that says that the random deregular graph with very high probability is Hamiltonian whenever d is at least 3. So somehow for us, this might seem a bit discouraging, because this means that for every value of d between 3 and n-1, the union of any deterministic graph with a random deregular graph is going to be Hamiltonian with very high probability, independently of the deterministic graph, just because of the random graph itself. And then somehow the only two cases where the deterministic part might play a role are when d is equal to 1 and 2. So it might seem that there's not much to say here, but we actually thought that these two cases were quite interesting. And actually what we have found is that the behavior of each of the two cases is very different from the other. So our main results are precisely what happens in each of these two cases. So I guess first, if we consider a random two regular graph, what we managed to prove is that if we consider any deterministic graph H with minimum degree at least alpha n, where alpha is something that's somewhat larger than log n over n to the power of 1/4, then with very high probability, the union with a random two regular graph is Hamiltonian, and not only Hamiltonian, but also pancyclic. So we contain cycles of all lengths. So somehow this should, I want you to think of this as analogous to the result of Bowman, Fries, and Martin, in the sense that for any constant alpha smaller than 1/2, the union with a random two regular graph with high probability gives us Hamiltonicity and also pancyclicity. And however, when we look at one regular graphs, random one regular graphs, in order to obtain Hamiltonicity and pancyclicity, even when we take the union with a deterministic graph H, we actually need the minimum degree of H to be at least √2 - 1 times n. So this is roughly 0.42 something times n. And this is sort of a sharp bound on the degree, in the sense that if you go below this minimum degree, you can actually build counterexamples such that the union with the random one regular graph doesn't even contain a Hamilton cycle. So for the rest of the talk, I'm just going to give a few ideas for how to prove these things. I wanted to start with this lower bound, so how to prove that the second theorem I just mentioned is best possible. And that will be this proposition here. And the idea is, well, we want to prove there is a counterexample for the positive statement. And we're just going to consider some unbalanced complete bipartite graph and use that to prove what we want. So the idea is that we're going to start with some complete bipartite graph. Let me draw something like this. So let's say that this part is called A and this part here is called B. And this is a complete bipartite graph. Sorry, something like this, okay? And the idea is that we're going to make A have size alpha times n, so that B is going to be 1 - alpha times n. And now if I ask you just on H, what is the largest cycle that we could find, you can probably imagine that we need to get, that we can get a cycle that covers all of A and it covers a similar amount of vertices in B. So somehow we should be able to cover something like this with a cycle. But there is a leftover of vertices here, this little bit here, which has size 1 - 2 alpha. My handwriting is terrible, sorry. 1 - 2 alpha. So now the question is, when we add a random graph on top, can we give some necessary condition for us to be able to obtain a Hamilton cycle? And an idea that you should have is that each time that I add an edge inside of here, this allows me to incorporate one new vertex into the cycle, because I can, so before it was just jumping from one side to the other and we have complete freedom because it's a complete graph. And now I can take one extra step inside of one part before going to the other and continuing as before. So that should tell us that what the necessary condition that we want is that the number of edges in the graph G inside of the set B should be at least 1 - 2 alpha. Now it's a matter simply of asking when can we guarantee that this condition holds. And okay, so here I'm only going to do an expectation calculation, but hopefully that's enough to convince you that this makes sense. So I'm going to take the set of all possible edges inside of G, and I'm going to compute how many I expect to find in a random one regular graph. And I'm sure that you'll be happy that the number of edges is 1 - alpha times n choose 2. And then a key feature of a random one regular graph is that if I just think about the probability of a single edge to be picked, you can just start from a vertex and pick one of its neighbors uniformly at random. So the probability is 1 over n minus 1. And this is roughly 1 minus alpha squared divided by 2 times n. And then the condition that we had, this necessary condition that I mentioned here, says that we are only going to hope for a Hamilton cycle if this is at least 1 minus 2 alpha times n. So what we have basically is an inequality here that we want to satisfy. And this inequality, when you solve it, it basically gives us this root 2 minus 1 that gives us the lower bound. Okay, so hopefully that part is clear, and then I can talk a bit more about the positive results. So I'm going to start with 2 regular graphs, and rather than giving an idea for the whole proof of what we have shown, I'm going to start with this somewhat simpler proposition. So I'm not going to talk about pancyclicity, I'm only going to talk about Hamiltonicity, and also the degree has to be at least log n over n to the 1 over 6, rather than 1 over 4, which was what I claimed before. And the reason for this is that in this range of alpha, the random graph is going to satisfy some nicer properties. So what properties I'm interested in, of course, one very important property for us is that when we take a random 2 regular graph, we can show that with very high probability, it basically consists of log n disjoint cycles. So a 2 regular graph is a union of disjoint cycles, and the question is how many there are in a random one, and in the random one, you basically get log n. And the second property, which is very important for us, is that we can show that for every pair of vertices in H, we can find many copies of this structure that I'm going to draw here. So basically, we start with 2 vertices. Let's call them X and Y. And what I want to prove is that X has some given vertex in H such that both of its neighbors in the random graph, so this red would be G, both of its neighbors are neighbors of Y in H as well. And this is not true if the neighborhood of Y is too small, which is why here I have given a sort of not tight bound on alpha. And the reason why these 2 properties are very important is very easy to understand. So I can give you a rundown of the whole proof now. The idea is that we're going to take all of these cycles that we have by the random graph, and we're just going to delete one edge from each of them. So we have a union of paths that cover all the vertices of the graph. And then what I'm going to do is I'm going to use the second property to iteratively combine these paths into longer and longer paths so that eventually I cover everything, and eventually I can turn a Hamiltonian path into a Hamilton cycle. So to give very basic examples, let's say that I have at least 2 paths, and then what I can do is I'm going to fix these 2 vertices, and I'm going to apply the property with these 2 vertices. And that tells us that I have some vertex here such that both of its neighbors are vertices, are also neighbors of the other vertex. So we have something like this. And then what we can do fairly easily is simply, at this point, this structure is involving 3 paths. And what I'm going to do is turn them into exactly 2 paths by doing something like this. So we reduce the number of paths by 1. And we could similarly be in a situation where we start with 2 paths. So we have something like this. And again, I'm going to look at these 2 vertices. But now, when I apply the property, it turns out that the edges are inside one of the paths. So let's say that we have something like this. And then what that tells us is that here we have this vertex has an edge to here and one edge to here. And again, in this situation, we can turn these 2 paths into only 1 path by choosing something like this. Yeah, so hopefully this convinces you that you can basically keep iterating this until you have only one cycle, sorry, only one path. And then by the end, when you have only one path, the idea is to use the same property again once more. So we start with a very long path. And now I'm going to consider the two endpoints, and I'm going to use these two endpoints to apply the property again. And this basically tells us that there's going to be some edge that goes like this, and from here it goes like this. And then we can again turn this into a cycle directly by just following first the path, then jumping to the other endpoint, then following the path, and then jumping to the other. So it's somehow a very simple strategy for proving that we have Hamiltonicity. Okay, and given that I'm running out of time, I'm going to skip anything about random one-regular graphs. I guess I should just say that the proof is more involved, and we need to use some structural properties of the graph that I've tried to explain them here in this lemma. But the basic core ideas are the same. So we basically construct a very large set of paths, and we join them into longer and longer paths until we can get a Hamilton cycle. And then to get pancyclicity, you just need to be a little more careful and make some modifications to the argument, but it remains largely the same. And I'll just finish with a couple of open problems that I'm interested in. So the first one is that I have told you that our result for one regular graph is optimal, in the sense that √2 - 1 is the minimum degree that allows us to get Hamiltonicity. But for two regular graphs, we actually don't know what's the minimum alpha such that this is true. So what we have proved is that log n over n to the power of 1/4 suffices, but we don't know if this is the minimum possible or whether this is very far. The best lower bound that we have is very far from our upper bound, so this would be an open problem. And then a different question is, I'm just going to think about a random one regular graph. This is just a random perfect matching, and a random perfect matching is a random K2 factor. So I'm going to generalize the question to random KR factors. So I'm basically saying, starting from n vertices, let's say for K3, I want you to pick a set of triangles uniformly at random that cover all the vertices. And then I'm asking for this random graph, is it true that there is some minimum degree for which, if you are above this alpha star, then you are guaranteed to have Hamiltonicity with very high probability. But if you are below, there is some sort of counterexample for this. So basically what we have proved in our result about one regular graphs is that this alpha star of 2 exists and is equal to √2 - 1. But I think the question is quite interesting for all values of R and perhaps for other graphs as well. And we have a conjecture for all other values of R, which is that this value exists and it should be given by the unique real positive solution to this equation that I'm showing here. And I'll just say that the lower bound, so the reason why we make this conjecture is that the same counterexample as for one regular graphs gives this bound here. So starting with a complete bipartite graph and adding this random KR factor on top gives you this equation here, basically. And I'll stop here. Thanks.